Good morning or good day, everyone. I refuse to use whether morning or afternoon for this such international participation of the workshop. So good day, everyone. Welcome to the third day of the NOAA AI workshop, the third NOAA AI workshop. And I want to welcome everyone to join our fourth plenary session today. And it aligns really well with the theme of our workshop this year, which is transforming weather, climate services, and blue economy with artificial intelligence. I'm Dr. Rao, a co-chair of the workshop. And before we move on to the exciting part of the plenary session, I want to remind everyone of the code of conduct and etiquette for this workshop. NCAI NOAA Center for Artificial Intelligence are committed to providing the participants of the workshop a safe, productive, inclusive, and welcoming environment for everyone. So if you're experiencing any intimidation or harassment, please report to the workshop planning group at ai.workshop@noaa.gov. In addition, I would like to draw attention to how you can submit your questions for speakers. If you haven't attended any of the previous plenary session before, you can go to slido.com to use the event code NOAA AI 2021 for submitting your question. And you can also just click the link that will be shared with you in the chat shortly to ask your questions. And we will address your question at the end of the session. If you can also upvote others' question instead of typing your own question. With that, I would like to introduce Dr. Rob Redman, who is another co-chair of the workshop, to introducing our distinguished speaker today.
Hello. All right. Good morning, good day, and good afternoon, and good evening, depending on where you are. And thank you so much, Douglas. Greatly appreciate that. So we're going to have a wonderful session today. We have an honored guest, Professor Stephen Belcher from the UK Met Office. He's the chief scientist there. And then after he gives his keynote, we'll have a panel session where Dr. Belcher and Jeb Stewart, who you've probably seen earlier along many times throughout this workshop, will be joined the panel. So without further ado, the bio. Professor Stephen Belcher is the Met Office chief scientist. As chief scientist, he has overall responsibility for the leadership and management of the Met Office's scientific program by providing strategic direction, ensuring high quality delivery, and nurturing scientific excellence. He represents the Met Office in science and research technology to UK government, ensuring that the Met Office science program fits properly into the wider UK environmental science landscape. In 2010, he became the joint Met Office chair in weather systems. This role gave him a taster of working closely with the Met Office, and in 2012, he joined the Met Office as director of the Met Office Hadley Centre. So welcome, Dr. Belcher. We look forward to your presentation. Please go ahead and take over the screen sharing. And
brilliant. Thank you, Rob, for that fantastic introduction. And I assume I'm coming through clearly to you now and you're seeing my opening slide.
yes.
So thanks, Rob. I mean, thank you to the organizers of this meeting. It's a really wonderful event, this, and the numbers speak for themselves. 1,300 attendees is really a fantastic achievement in this area. It really demonstrates to me the importance of getting AI into the weather and climate kind of services realm. So I was delighted to be invited to give this keynote, and it sort of forced a bit of reflection back at the Met Office amongst my team on what we've been doing over the last few years in trying to embed data science.
Sorry, you are muted right now, Stephen. Can you unmute yourself?
I am. I'm not sure what happened there. Shout out if that happens again.
You're good now.
Thank you. Yeah, so what I'd like to do in this presentation is really share our experience of building AI within our organization and some of the challenges that we've met along the way. We're definitely not fully down this path at the moment. So I'm going to share some of the difficult bits, and I look forward in the panel discussion to hearing about others' experience in some of these areas. And then also a sort of nod to the future towards digital twins. So let me just start at the beginning, and forgive me if this is overly basic. So how do we make a weather forecast or a climate projection? Well, a weather forecast starts with observations of the atmosphere and the oceans and the land surface, so that bottom left-hand square. We combine those with a simulation tool, and here I'm trying to use words carefully. So by a simulation, I mean a model of the atmosphere and the oceans that's based on the laws of physics. So the Navier-Stokes equations, the conservation of energy in some form, conservation of moisture, etc. We then take those partial differential equations, we tessellate them across the atmosphere and the oceans, we finite difference the PDEs, partial differential equations, and we step forward in time. So that's the simulation part. The output of that simulation is then an analysis platform. And depending on whether in the weather realm or the climate realm, and in the UK Met Office, we have responsibility across all of those timescales, we do various bits of analysis. So if it's on the weather realm, we'll do post-processing of that numerical weather prediction to try and correct for biases, downscale it to special locations, etc. If it's a climate simulation, we may combine with other data sets to understand various risks. And I'll come back to that. So we've got the analysis platform, and then from there we perform the analysis and we squirt it out into a range of services. And they may be the broadcast weather forecast that you're familiar with seeing on TV, or it could be more specialized forecasts such as aviation tracking and high-level winds in the atmosphere to save fuel, or it could be for military operations. It's a whole raft. We deliver, like in the US, thousands of forecasts every day to different applications. So that's what we do. Here's a snapshot, and this is just a pretty picture, or two pretty pictures, of the kind of thing we now produce for a weather forecast, a numerical weather forecast. And one of these pictures is showing the output from the simulation tool, and the other is showing the output from a weather radar. And this is rainfall rates in millimeters per hour for a particularly heavy rainstorm. It's from July 2012, as it happens. And I hope you'll agree, they look pretty similar. The level of detail encapsulated in these simulations is really quite remarkable, and it's capturing those really high rainfall rates. Of course, there are differences, and I could give you a whole lecture and we could have a whole panel discussion on that. And actually, I'm going to pause there and say it's the middle of the afternoon here, and it's a lovely sunny day, and therefore my fan has decided to kick in. So if it gets too intrusive, maybe one of the moderators could step in and say so. Apologies for that. Okay, so that's what we do. Question now is, how does AI fit into that? And as I tried to emphasize before, I'm using words carefully here. So by simulation, I mean the solution to partial differential equations, the laws of physics, etc. AI, obviously, machine learning is a data-driven form of modeling. How does that fit? How do we fuse that data-driven modeling with this simulation? And so along the top of this slide, I've kind of repeated that value chain of observation, simulation, analysis out to products. And I'm just trying to think through that value chain where AI could help. And I was very excited to see Peter Dubin from the European Centre for Medium Range Weather Forecast, also a UK or pan-European weather forecast agency located in the UK. And I know Peter speaks about the role of AI in a very similar way to this. So if we start on the left, then we've got all these observations, and there's a whole ton of ways in which AI can help us with that. And I'll show you a very specific example that we've worked with later. So quality control, actually, we don't use all the data we can get. So we thin the data. And so are there smart weather dependent ways of doing that? At the moment, we use a static algorithm. It could be that when it's, I don't know, the winter, or when it's a very mobile situation, we should thin in a different way compared to if it's a more static blocking. We don't know at the moment. Gap filling in observations, very important on the climate problem, for example. So you can see that just the observations past this is a very rich area. Now, again, forgive me if I'm telling you stuff that I'm sure you're deep experts in, but the way we fuse the observations with the simulation is through a mathematical technique that we refer to as data assimilation. And it comes from a branch of maths called control theory. So this is a way effectively of projecting the observations onto a solution to the partial differential equations that we're solving. So it's kind of filter on the data to make them suitable to initialize the weather forecast. And actually, in the weather prediction, a big part of our compute power is used on this data assimilation cycle. So there's quite a bit of interest in seeing whether there are clever ways that AI can emulate the data assimilation or part of the data assimilation cycle to make it more computationally efficient. Moving again to the right, the actual simulation itself, when we first started talking about the use of AI, everyone immediately thought, oh my God, Stephen Belcher, he's the new chief scientist, he wants to chuck out all those simulation tools and do the whole forecast using AI. That would be a very extreme reaction to this, and my presentation is deliberately entitled Fusing Simulation with Data Sciences. So that's a very conscious decision. So on the simulation itself, there are things that people are trying out there, and actually this workshop has got some great examples of this. When we do the simulation, we solve the partial differential equations, but there are some processes which are too small to resolve explicitly. So clouds is the classic example. The interaction between the land surface and the atmosphere is another. Aspects of the ocean, which is my own area of research, the mixing in the ocean needs to be parameterized. And so there's the possibility of building emulators that are more computationally efficient than these so-called parameterization schemes that we can then build in to make the simulation tool itself more efficient. I've also recently seen some very neat work that shows that deep in the guts of the numerical algorithm that actually solves partial differential equations, these are ultimately matrix manipulations, there are some really neat AI algorithms that maybe can precondition the matrices to speed that bit up. So that's all about increasing the computational efficiency of the simulation tools. The simulations themselves, in the climate realm already, because running climate simulators is so computationally demanding, we actually build emulators of the climate model that emulate and output a very small number of the climate model outputs, such as global mean temperature, maybe regional temperatures and some other variables, so that we can build a bigger ensemble of potential futures to give a better quantification of uncertainty and so on. So that's actually quite a mature field in the climate world at the moment. We don't do that in the weather world. You've got to ask why not. And then the other obvious example here is what in the jargon is known as nowcasting. So in the very short term, in the next hour or 2 hours, particularly when we've got very heavy convective rainfall events. So convective rainfall is convection that bubbles up, maybe organizes, but gives in the UK and Europe, and indeed in Northern US, North America, excuse me, the heavy rain-bearing systems in the summer. Models can do that, but in those first few hours, actually data-driven methodologies probably beat those. And so we've been putting a lot of effort into taking radar pictures of the rainfall, which are 3D time-evolving radar imagery, and using that to drive data-driven nowcasting. And then finally, on the right-hand side, on the analysis side, and forgive me for going through this in such a stately manner, but this is, for me, one of the really key slides here, is understanding this richness of how we can fuse machine learning with simulation. And I hope we can have a discussion about this in the panel session. Okay, so the simulation spits out a bunch of numbers. We do stuff with that in the weather realm. We call it post-processing. We do bias correction and stuff like that. And again, I have an example later. In the climate realm, we do other things. And then finally, and I think here really is a very interesting realm, what we do in my world is to predict or project or forecast the hazards. So will it be windy? Will it be raining? Will it be cold? Those are the weather hazards. Increasingly, what our users demand are the risks and impacts associated with those hazards. And so mashing up our hazard information with impact, so vulnerability and exposure. So to give you a very sort of simple example, but kind of an interesting one, if it's windy, there are roads in the UK where the traffic is susceptible for high-sided vehicles to be blown over. So the hazard's the wind. The exposure is what kind of vehicles blow over in certain wind speeds. And then that's the vulnerability. And then the exposure is where are these vehicles? And so bringing those data together, we can make a live tool that tells us what that risk actually is. So as I say, forgive me for going through that in some detail, but I did just want to sort of flush out that this is kind of an interesting area. Okay, so hence my term, fusing simulation with data sciences, and that's really our kind of guiding principle in the Met Office. We're not trying to replace current weather forecasts with machine learning or data-driven techniques. It's all about that fusion. Okay, so say a few words now about how we've gone about actually embedding this within the Met Office. Actually, we were very influenced by the Coursera advice that's free online. And there's the AI transformation playbook given in that. And there were really 5 steps that we followed, guided by this AI transformation playbook. So firstly, we launched some pilot projects, and I'm going to give you 3 examples of those later. Secondly, we've developed or are developing an in-house AI team, and I'll say something about how we did that structurally. Partnerships, we were talking ahead of the presentation about what the kind of goals of the workshop and perhaps my personal goals around this presentation. We're at a fairly early stage in the Met Office in really building this capability. So we are looking for good partners to work with. And this workshop, therefore, was a great opportunity to kind of show what we're doing and try and build some new partnerships. Training has been a really big part of our effort. And then last, and the Coursera playbook explains why you do this, develop a strategy. There's a great tendency, we've got this great new thing, machine learning, let's write a strategy. And the strong encouragement in the playbook is to do some stuff and co-develop the strategy along the same line. So what you're seeing here is early days on that strategy. Okay. So I'm going to give you 3 examples just to sort of whet your appetite on what we're doing here. And I should say that the authors of these, I believe, are in the audience. So to those authors, I hope I do your great work credit, and thank you for your material. So this is a first example, and just looking at that value chain observation, simulation, analysis out to products. This is work led by Stephen Haddad in our informatics lab that is really on the observations side. And this piece of work looked at ocean floats, so-called XBTs, and these are floats that measure temperature profiles, or they used to, in the ocean. And top left shows the number of those floats that were launched through time. So you can see that during the 70s, 80s, 90s, these were really a big part of our ocean observations, slightly declining now as the technology is being replaced by other things. Why do we care about ocean temperatures? Well, one reason is for climate. So the temperatures give us an estimate of the heat content of the ocean, and then having a time series of that helps us understand where the heat associated with global warming is going, because 97% of the heat associated with global warming is stored in the ocean and of course leads to sea level rise amongst other things. So really getting a nice, clean, reliable ocean heat content time series is a really, really important element of climate science. What the top left plot shows is that the red, so a big fraction of these XBTs were unlabeled, meaning that the specific model and type of XBT was unknown from the metadata. There were mechanisms that were rather labor intensive to identify those, and it's rather important to understand which XBT you've got because there are bias corrections which differ depending on the model. And Stephen and his colleagues listed below developed a machine learning algorithm to do that, a sort of decision tree machine learning algorithm. And this has proven to be really spectacularly successful, and it's enabled us to really build that, that ocean heat content record in a much better way. So I thought that was a really neat example of how we might apply it to observations, and there are others, but here's something that we did reasonably quickly, actually, Stephen with a small team. My second example is really on the simulation side, and I have to say, so my own expertise is in physics of the ocean and the atmosphere, and I've done simulation stuff. I've written modeling tools, simulation tools. What I hadn't thought about is, okay, we developed some fantastic new machine learning algorithm that maybe represents one of the processes in the model that we want to speed up using an emulator. What Sam Adams recognized that, okay, you've got the machine learning algorithm, but how are we going to plug that into the simulation tool? Because lots of the machine learning is done using a stack of tools like TensorFlow or PyTorch or whatever, using Python interfaces, whereas we still write our codes in Fortran or C++. So the relationship between those two things needed a bit of work. And so Sam really did a really, really nice piece of work, just digging into some of those packages on the back ends to build a tool that could take the output of TensorFlow or PyTorch or whatever and enable us to plug something into the simulation tool. And as a demonstrator of this, in the jargon, the radiation package in our simulation tool. So this is the bit that computes the incoming solar radiation and the outgoing long wave radiation, which is fundamental to what drives the whole weather and climate system, including clouds and all that kind of stuff. So we have and that's was a very expensive part of the code. We now have a machine learning built emulator, and Sam demonstrated how that could then be plugged in to the code. So we're about to go live with that emulator right now. My third and final example is on the analysis element, and this is on the post-processing. So this was work led by Aaron Hopkinson, and it speaks to some of the performance targets that we face when we're in an operational organization such as the Met Office. So we are compelled by our funders, the UK government, to have a good fraction, a named fraction of our forecast within 2 degrees, so for our surface forecasts. So the simulation tool produces a numerical simulation estimate of those tools, but there are various very detailed surface, my slide automatically moved on there. Let me just move back briefly to Aaron's work. We do post-processing because there are very detailed things that make local climate or local weather, which the model can't capture. So Aaron built really impressively quickly a neural network to build on the things we were doing already in this, and showed really quite remarkable improvement in our forecast skill for this particular metric. And I think this application really caught the attention of the organization. The other 2 examples are really important, but they may be slightly upstream of where our Met Office commercial director may have been interested, but this caught the attention of the whole organization. Okay, so those are the pilot projects. So how are we beginning to embed these techniques into the organization more fully. And there are really two sides to this. Firstly, the structural side, and secondly, the people side. So on the structural side, we initiated a team within the Met Office Science and Technology team. So we have within the Met Office is about 2,000 staff. 1,000 of those sit either in technology or in the science directorates, which are my responsibilities. So we built this joint team that we call the Informatics Lab, who are specialist data scientists to really bring the skills in. And I think given time, I'll just pause on that. The way that we're looking to try and deploy the data scientists, I think may resonate with an earlier plenary that you had over whether you bring in expert data scientists and then teach them about the domain, or whether you take domain scientists and give them the AI skills. We've kind of got some thoughts on that I'd love to talk about. So that's our specialist workforce. The second thing we did was we, next to us, we're based down in the southwest of the UK, next to us is the University of Exeter, who have great skills in data sciences and AI, particularly applied to environmental problems. So we've also launched a joint centre with the University of Exeter, and it's the Joint Centre for Excellence in Environmental Intelligence, so environmental data using artificial intelligence. So it's environmental intelligence, get it? My colleague, Kirstine Dale, is the co-director from the Met Office side in that, and I believe has been part of your organising committee for this workshop. So those are two structural things to give this a place and a home. The second element of this is the people side of this. So with people, you can either buy people in, so recruit in, or you can build, build the competencies within people you've already got, or you can borrow through secondments and partnerships. The buy is difficult. As a government lab, we can't compete with some of the startups in this area. Some people are drawn to organisations like the Met Office to come and work with us because of our mission. But we found building, so training, and communities of practice, which again, I think is a very important element of your workshop here. And then secondments and partnerships have been our more effective tools. So again, happy to pick that up in the questions. I'm going to pick up the pace just a little now to give us a nice long panel discussion. But on the training, I did want to just highlight one thing. We did training for the executive directors of the Met Office. And this was a recommendation that came out of that Coursera playbook that I mentioned earlier. So the idea here is it's a pretty top level description, but it talks about what can AI do and what can't it do? Because there's a lot of hype. I don't need to tell this audience, a lot of hype around AI. And it's terribly easy to say, oh, we can't forecast fog. Let's get AI to solve that for us, please. But, you know, maybe fog can be solved by AI, maybe it can't. So there's some expectation management here. The other side of it is to emphasize that AI potentially can reach whole areas of an endeavor like the Met Office. So reaching the highest levels of an organization we felt was very important, and I think that was a big step. You can see that there's training on the domain expertise, which we've done with a range of people, particularly in the UK. We've used AWS training. We've got so-called apprenticeships at the master's level with various universities. And we put a lot of effort into communities of practice, and I'm delighted to see that those are being talked about in this workshop. And then partnerships, we're still building these, mainly in the UK right now, but we are looking to reach out internationally. So as I say, great that I got this invite to speak here. Okay, and I think I'm going to make this my penultimate slide. So I did want to just say a few words about what next. So I've really focused here on AI, on the value chain that we have in the Met Office. And I want to emphasize that's the value chain both for weather and for climate applications. we're by no means finished on embedding that. We are some way, and let's talk about it in the panel session where what we need to do more. But it's getting that toolkit really embedded. For me, the next thing is digital twins, and how does that change what we're doing now? And I've taken this figure from the IPCC's 5th assessment report. So the IPCC, you'll all know, is the Intergovernmental Panel on Climate Change. So this is the organization that synthesizes the evidence for a changing climate, for the fact that that change is due to greenhouse gases, and it talks about the impacts of climate change through Working Group 2 and strategies for reducing emissions in Working Group 3. And what this diagram shows is really that risk framework that I touched on earlier. So the 3 ovals here represent the hazard. So these are weather and climate events. The vulnerability, so if we're thinking of overheating and the impacts of health, the vulnerability might be the different vulnerabilities of different elements of the population to heat stress. And then the exposure is, where are these people? Which parts of the country? What kind of heat are they therefore going to be exposed to? And by bringing those data sets together, we then get the risk. So the risk here is the risk of heat stress amongst the population. So first off, we've been building a tool through the Joint Centre, which we call CLIMAR, that is a tool that brings together data sets to produce that risk estimate, CLIMAR. And I actually think this is a really exciting development. It sounds really simple to do this, but it brings enormous kind of rigor to the thinking. It also brings rigor to the thinking on where do we partner. In my world, in the Met Office, in weather and climate, we know about the weather and climate events. We are not medics. We do not know about the vulnerability, what populations get heat stroke. We don't know where people are, but we, in the UK, for example, have an Office of National Statistics who know darn well where people are and how they move about. So it gives you that partnership framework. Where does digital twins come in? It's really the 2 arrows here. So the arrow coming out of the disaster risk is to disaster management. So the way that we manage the impacts of climate change is to build resilience through changing vulnerability and/or exposure. So in the heat stress example, we may change the way we build our buildings to limit the exposure to the extreme temperatures, or we might give health alerts so that vulnerable people can move to safer locations. So that's changing the exposure and thereby reducing the risk. We know that the weather and climate events themselves are changing because the climate is changing. The climate is changing because of increased greenhouse gases. So if we can reduce the greenhouse gas emissions and stabilize climate, we will stabilize the weather and climate events that we get. If we don't, those will continue to change and we change the risk. So to me, with some commentary, this diagram begins to speak to digital twins. It's closing that loop. It's converting the hazards into risks, and then it's closing the loop from those risks into action that can then begin to address and either reduce or build resilience to those risks. So I could have given a whole lecture on digital twins. Our thinking on these is at a pretty early stage. There are other industries such as manufacturing that are much more advanced than we are in this realm. But to me, this has to be the way forward, because it's in the climate realm, science has shown us the problem, and all of our world leaders accept that. And the UK is hosting the Conference of the Parties, the COP negotiations, which will be our world leaders coming together to tackle climate change in just 6 weeks' time. The science community, our community, is as we've got the message over. Science has told us what the problem is. Science now needs to be part of the solution. It seems to me that digital twins could be a really important digital tool to help us close that loop from problem identification to problem solution. I'm just clicking on now, so I'm going to skip these slides, I think, and I'm going to go to my summary slide. So what are my main messages here? My main message is that in the last 3 or 4 years at the Met Office, we've been really trying to get AI into the Met Office as one of our key tools to complement our simulation and other tools that we have right now. And our watchword is fusing simulation with data sciences. It's not replacement. We've gone through this Coursera playbook, and we've done some of the stuff that's recommended there. Kirstine Dale and her team in the informatics lab are now building on this to give us more of a strategy. I'd say we've still got some way to go in really building the core AI expertise, and I'd love to talk about that more. Our team at the moment is subcritical, and we're looking actually to double the size of that team in the next 6 months. We do need to build more partnerships because we recognize that this is a fast moving area and we want to keep up with everyone else. And at the same time, we think we've got some great problems. We've got some fantastic data sets. The Met Office produces several tens of petabytes of data every day. And it's nice and clean. It's got metadata, you know, it should be a great playground for AI. And then finally, for me, AI is one of the elements that gives us the potential for digital twins. Observations, simulation, the platform and technologies associated with analysis, which of course includes AI as one of the tools, is the basis for a digital twin. So I think with that, I'll stop and look forward to the discussion session. Thank you very much.
Professor Belcher, this is Rob again. That was really brilliant. Thank you so much for sharing with us and kicking off our 3rd day of the workshop, the end of your working day. And I just want to say, you gave me 2 homework assignments. I have a homework assignment to check out this Coursera AI transformation playbook. I'm going to do that right away. Appreciate that. And the second one is to convince you to offer a future lecture on digital twins. You sort of planted the seed for that. I really appreciated the careful language around fusion versus replacement, which sparks concern. And fusion is absolutely, of course, the right and consensus approach. And then finally, we have developed a partnership with your lovely team who is supporting this workshop in so many ways and working on collaborations with us. So please convey our gratitude to them as well. And it was great to see their work here also in your presentation. So we're going to assemble our panel now. And so just a shout out to our audience to go ahead and use Slido to post your questions, upvote, downvote, to help us make this panel discussion awesome. And I want to introduce our second panel member here, Jeff Stewart. He is with NOAA's research arm. That's the Office of Oceanic and Atmospheric Research, or OAR. And he's the co-chair of NOAA's AI Executive Committee. He's heavily involved in exploring and supporting AI applications for NOAA and developing critical partnerships, such as with the new U.S. National Science Foundation AI Institute for research on trustworthy AI in weather, climate, and coastal oceanography, also known as AI2ES. So welcome, Jeb. It's a great honor to have you join us here today. So I'm going to go glance at the questions and see what's popping up for us. And let's see. Yes. So someone took the bait here. This is a person who is curious about the issue of bringing data science experts and explaining to them about the domain knowledge, the Earth system science domain knowledge, versus teaching AI and ML to a domain expert. The experience of this question asker is that the latter of teaching ML to a domain expert has more chances to be successful And I'll pose this question to both Stephen and Jeb. We'll start with Stephen. What are your views on how we merge data science and Earth system science subject matter experts?
Well, I'm really grateful for the person who did pose that question. I mean, on a pragmatic level, we have found that the more straightforward way because it's the build solution. We found it more difficult to recruit people in with the expertise. I think the thing I would add is I had a very influential conversation with a colleague of ours in the Netherlands called Wilco Heeslegger, who used to run the Netherlands E-Science Centre. And their model was they had a team of AI experts in the mothership in the E-Science Centre, and they'd loan them out to science domain expert teams to work on projects. And the AI expert would spend 3 or 4 days a week with the domain experts, say with the astronomers, learning how to use AI or working on a project on AI and, I don't know, galaxy recognition. And then 1 or 2 days a week back at the mothership being a data scientist. And so actually our vision for the informatics lab in the Met Office is that we follow that pattern. Now, we haven't quite got there yet, and I realize I'm answering a slightly different question, but I'm pretty excited by this model, and I stress we haven't got there yet, but that's really what I'm hoping for.
Thank you very much. I'll ask Jeb if you'd like to share anything on this topic as we start to build our community of practice around AI for NOAA. You have thoughts on kind of that, what is that composition? What's the best composition look like? I think Jeb's screen is frozen on my side, so we'll pause for a second just for the technology to catch up to us.
I think I'm back, but I missed the last part of the question there.
Oh yeah, I was just going to see if you wanted to share your views on what's the balance of bringing data science expertise in with our Earth system science experts as we build the community practice around AI for NOAA? Yeah,
so I agree. This is a great question, and it's a problem we struggle with. And I think there are very few people that speak both languages efficiently and fluently. So for our perspective, it's been very helpful to work with the domain.
Maybe Deb, I've lost your voice. Your voice cut out for a second there. You could go back.
Partnership. Oh shoot, I'm breaking up again here. So my technology is not the best this morning.
It's okay right now.
If you can turn off your video, that may help.
Sure. Yes. So I don't know where you lost me here, but I think that the key point I think of this perspective is really this community of practice, because we can't do it alone. We don't have the knowledge and expertise, and we have seen times when we've trained people up on machine learning and they leave to other industries. And so one way to bring them back is through these partnerships. And so whether through universities, through private sectors, I think it's important to maintain the community of practice across the spectrum here to help bring the expertise back in no matter where it exists to help us with these projects.
Thank you, Jeb. And you planted the seed I'm going to take with. We have a new website. It's noaa.gov/AI. And if you go one more slash to training, or just click on the training tab, you'll see our team's first gap assessment on the training needs of the workforce. And it touches on a lot of the things that you're saying here. How can they become trained and become AI ready? All right, so let me go to next question here. Let's see. Okay, so this one's to Stephen first. Thank you for discussing the importance of machine learning for emulations and post-processing. Are there any worries that using machine learning makes the modeling less transparent or explainable? And how is this addressed at the UK Met Office? We'll do a follow-on question about trustworthy AI after this.
Yeah, again, that's a really excellent question. So I have I don't know if Aaron is on this call, Aaron Hopkinson, who did the post-processing work. We had a an interesting experience with that. So we take the weather forecast, we have this post-processing neural network algorithm for the site-specific temperature forecast. And I think it was earlier this spring, we had a pretty hot spell, and the machine learning algorithm was saying we were going to break records. And in the Met Office, the numerical output goes through a layer of human forecasters who got rather nervous about this, and they actually downgraded the forecast. Now, as it turned out, the machine learning algorithm was closer to the observed temperatures than the downgraded forecast. However, it would have broken a record, the forecast, but the observations did not. So who was right, discuss. But it kind of, I think it exposes this problem that there's something about the physics-based simulations that people kind of have grown more comfortable with, whereas the whole AI black box thing is difficult. And I would add to that, and again, I'm going off topic, maybe rambling a bit. We update our weather forecast simulation system once or twice a year. And so we have to retrain the machine learning every time too, right, to the new system, because the new system has different biases. So there's a lot in there in that black box question, and maybe I've exposed just one or two of them. There are clearly jeopardies. If we had replaced our simulation tools with a machine learning algorithm, I'm not sure we'd know about climate change. So, you know, there's a place for the physics there, and hence my constant mantra, which I hope I'm not boring you with yet, fusion of simulation and machine learning. So yeah, it's a really important one. And we had our first conference that the Joint Centre hosted last November, and Libby Barnes gave a really nice talk on explainable AI. And I think for me, that's a really interesting kind of development of the machine learning technologies.
Okay, thank you. Yeah, I'll say, Jeb, would you like to add any comments on this vein? And then we'll go to a question that takes trustworthy AI into the social sciences a bit after that.
Well, I was going to maybe bridge that gap here a little bit as well. So we'll move into that topic. Yeah, so, you know, trustworthy AI, there's the aspects of explainable AI, what's going on within the model, how do we explain it, but there also is how we communicate. I think, you know, this brings in the social scientist aspect here. So we can explain it all we want, but only our experts might understand that explainability aspect. So talking to our end users and how they receive that information from these AI models is also an important aspect. I would look back and say that, you know, we have trust in our current systems because we've used them for a long time, and they're somewhat based on physical approaches. I think there's another aspect of AI, the physics guided approaches, where we introduce physics into the training process itself that helps kind of put guardrails, so to speak, so it behaves more like physical models, is another aspect that help with the trustworthy AI. And so we're seeing a kind of a growth and explosion in that area for the physics guided approach here. But there's multiple different angles, I think, to approach this explainable and trustworthiness of the AI. And one thing that hasn't been brought up a lot, well, it's been brought up in this week at this conference, but we haven't talked about it much in this section, is that social scientist aspect. And so continuing along that vein, I see other questions here, Rob, I might be leading into.
Yes, you're leading you're leading me. That's perfect. So I would like to ask a follow-up question to Stephen along this topic. And it's one of the questions posed, but I'm going to just adjust a little bit, which is risky, but I think it'll work. So how do you have thoughts on how we can introduce more social scientists into the mix so we can fill many of the human element gaps that might come up using AI ML methods and operations? And I think you ended on a lovely slide that started to speak to that point in disaster risk management.
Yeah, this is a huge topic, of course, and the COVID epidemic, of course, has spoken to this very vividly, that, you know, be it behavior, do people follow the lockdown rules or not, has a huge impact on the success of them. So in the UK, this is a very, very live topic, partly for that reason. And then again, because we're hosting COP, that mentality is coming into the climate kind of realm. Clearly we need to get into this more. I'm not sure I have hugely profound things to do. I'm really looking forward to hear what Jeb has to say to this. I mean, we're onto that partnership thing again, and I feel slightly trite saying it, but we've already spoken about the AI versus physical model or weather and climate domain expertise. We now need that additionally complete the orthogonal axis, maybe, of the behavioral sciences. We've done a little bit on the, for example, on the weather forecast side. So we issue national severe weather warnings, and they have a risk and impact matrix, and that the communication of those had quite a lot of behavioral scientists involved. But when we move to the digital twins, we're moving that such an enormously higher level. It's quite scary. So Jeb, please help me. What could I do now to smooth that?
Sure. Yeah, this is where I'm going to put on my hat with our partnership with the AI2ES, the NSF Institute, because we have social scientists as part of this collaboration and partnership. And I think there's a couple different aspects here. One, even internally, sometimes we don't agree how we use the terms and terminology for even explainable AI. What does this mean? How does this represent things? And so they can help us with those aspects. And then when we talk about the impacts, our partners sometimes only care about when's it going to start, how bad is it going to be, and how long will it last. You know, those are kind of the basic questions about any impact or risk that they're looking at. So taking information from our AI models that are produced, that can produce probabilistic information, gives them a wide spectrum of answers about the possible solutions. So how do we synthesize that information? How do we process the information to communicate what this impact or this risk is that our model is saying? And there's a very fertile ground here for additional research about how we talk to our partners. So there's multiple levels of partners. We have the partners within our AI2ES, they're working jointly on researching these topics, and then there's partners who use the information that comes out of these things. And so in terms of interacting with those partners that are the end users of our products, there's a lot of social science that needs to happen in order to best communicate what our model is saying and what it means towards this particular impact. Just because it says that particular risk or impact is triggered isn't the whole story. There's a lot of information behind there about why it's getting to that level, the information that led to that was put into the model in the first place. And so I think social scientists are really in a good place to help us understand that full spectrum. The data goes into the model itself, and then the products that come out of it. So it's definitely an area that I think, and I hope to see more talks about that in the future at future workshops. And so it's, yeah, big subject, and I don't have a lot of information. It's not my background, but I see a lot of potential there.
Well, could I just come back with another comment? And Jeb, I too will follow this with huge interest and look forward to learning more about your teams on this. The climate change and pathways to net zero is this writ large, it seems to me. We are developing new technologies, but it's going to be about uptake and behavioral side to actually get folk to adopt these new technologies. So if we wanted a more kind of stimulating motive for doing this, I know of none other that's more kind of profound.
Exactly. Yeah, we have our short-term risk, you know, where a thunderstorm might develop this afternoon, and we have the longer-term risk related to climate. There's a lot of, it's a very broad spectrum, and I think there are a lot of areas that this is challenging us.
That was a brilliant discussion, and I will take this on, and I'll suggest there are two great plenary opportunities. One is plenary session 7. They're both on Friday, by the way. It's plenary session 7 is integrated and interdisciplinary AI development for environmental sciences. There we'll touch on the social science part of it significantly, as well as plenary session 8 on Friday. That's part of our closing plenary, and it's diversifying the future workforce of AI and environmental sciences. We'll figure out who are all the people and types of people that need to be brought into the conversation at the beginning of an AI and ML venture to ensure trustworthiness and responsibility and equitable access to the services that are created. So those are two plugs for upcoming plenaries. We only have 5 minutes left. I'm going to go to a question that's been highly upvoted and also near and dear to my heart, coming from the stewardship and archive side of NOAA. And this question poses, could you share your perspectives on how AI could help address the data deluge So you mentioned in your slides the Internet of Things and all the different platforms that we're going to fuse together to solve problems. So could you talk about how AI might, a little bit more about how AI might be brought to bear on this problem? And so with the tens of petabytes flowing in each day, could AI be used in clever ways to compress the data in situ or otherwise? So to Stephen first.
Gosh, that's a really big question. The data deluge. So I guess one of the, again, this is a slightly oblique response. For sure, we're having to change the way we do analysis of data in the Met Office, which is why I deliberately have that analysis box in my value chain. And the analysis tools need to go to the data now, but that's well known to this community, but maybe less well known in my home community. I guess one example from the weather side would be that when we make a weather forecast now, we actually do 50 simulations or so and generate a Monte Carlo ensemble of forecasts. And so for the human forecasters, that's kind of a lot to take in. And so using some kind of pattern recognition tools to help us latch on to the ensemble that may be tracking reality. So we update the forecast only periodically, and the real atmosphere is continuous. I understand, I'd ever go there. So, you know, between forecast updates is one of those ensembles actually closer to reality. So could pattern recognition help there? The compression side, I'm not a computer scientist, so I hope so, and please tell me if that is true. On the climate side, I mean, we're kind of verging now into the discussion around data versus information, aren't we? And to me, maybe that's kind of what digital twins are trying to do. They're trying to produce an analysis platform where you don't need that deep domain expertise to play with the data. And so for sure, there's got to be some machine learning tools that are going to help us play in the data lake.
I love that concept. Data lake, being at NOAA, I'd like to rebrand it Data Ocean. Thank you, Stephen. And I'm reflecting on your value chain model and some of the ideas in there, and it makes a lot of sense. And also kind of tying this back to the first plenary, Dr. Spinrad mentioned, it will be very insightful to see where edge computing takes us, the computing that is done on the observing system itself. Jeb, would you like to add anything to this topic as well?
I was just going to emphasize some points that Stephen already made in terms of like the automated labeling. So as we get the classification, the segmentation type activities that AI is traditionally pretty good at, have a lot of ways to help us with this data deluge. They can automatically label so people can go back and check out historical records and find things of interest that may have been labeled for their particular cases. So I think exploration in that area for AI helps, has some promise for the data deluge. Another aspect is just the overall faster processing. There's another question coming up, but maybe potentially about this, but AI has shown promise to be able to faster process. And so as we're collecting more and more observations from different platforms, from different systems, being able to find out, you know, if there's biases in those data, correct those biases, as well as throw out or quality control of these type of observations. I think there's a lot of potential with AI in those aspects for just processing incoming in situ type observations. There is some work I have seen on terms of compression, but I think there's a lot of other areas that AI has potential to help us with this data deluge. And it's just the processing and this automatic labeling, I think, are the two big aspects that can help.
Oh, that's a wonderful endpoint there, automatic labeling. Yes, thank you so much. So we had a wonderful conversation, and as always, we never have enough time. I just want to thank Jeb and Stephen here for carrying us through a lot of excellent terrain in this space, and I hope you both enjoy other aspects of our workshop and look forward to developing greater partnerships with UK Met. I'm going to hand off now to Douglas, who is going to guide us onward into the workshop today.
Thanks, Rob, Stephen, and Jeb for a great discussion. And I just want to Remind everyone this conversation doesn't need to end right here. So we have a Slack space with the channel 01_workshop. And you can already find some links in there that have been mentioned in this discussion. And please join us in the virtual coffee hour happening at 11 Mountain Time. And today we're going to focus on the wish list of AI and machine learning projects given no limitation of funding or the resources. So just imagine big what you can do in the wonder space. And we have another upcoming plenary session for today, which is 1:30 Mountain Time with Dr. Laura Zena, and who is a professor from New York University. She will be sharing her vision on AI for ocean sciences. And last but not least, we really encourage everyone to join the virtual poster walks in the Kiko chat space, where there's no password needed. And please join our session 4 of the virtual posters at 4 p.m. Mountain Time. So, and again, please visit noaa.gov/AI to find the most recent news about NOAA Center for Artificial Intelligence. And thank you again for joining this session, and we'll see you around in the different sessions.